Good. Thank you all for the well wishes, by the way. But yeah, it was an interesting experience. So the plan for today is to finish up on proton NMR spectroscopy. We were kind of in the middle of simple splitting, which I think is what you're going to run into most of the time. Maybe not 100%, but probably at least 90% of the time. The splitting patterns you see will be relatively simple to explain using this kind of n+1 rule. But I want to at least make you aware of some of the situations where the simple n+1 thing doesn't hold. So we'll go through some examples of that. As always, I'm not going to be able to show you every single possible thing that can happen, but I think I can show you the main ones that you might run into. I do have some reef polling questions today, finally. I have one on chapter 23 stuff and one on NMR material. And then with the other class, I had about 4 or 5 minutes left, which if I had to guess is going to translate into about 7 or 8 minutes left for you guys, since things usually go a little faster because I have all the structures drawn. So what I might very well do is just start chapter 26 on carbohydrates. We won't get as far as glucose and all the different ways to draw glucose. That can wait until Wednesday. Yeah, but if I can at least get you guys used to the idea of Fissure projections, of DNL glyceraldehyde, which are up there with dihydroxyacetone, the smallest molecules that we really can consider to be sugars, and therefore the simplest ones. And if we can get that far, I'm happy. I'll save the more complicated stuff for Wednesday. So last time we ended up with diisopropyl ether and p-anisaldehyde. I just picked them as examples of compounds that undergo or that display simple splitting in their proton NMR spectra. And we already went over these two compounds. We pointed out how there's 2 types of hydrogens in diisopropyl ether. One of them are these blue hydrogens, of which there are actually 12, but since the molecule is symmetrical, rather than getting a ratio of, rather than seeing 12:2, we'll see 6:1, which is of course the same ratio. But that's why we see a 6H resonance and a 1H resonance. These 6 hydrogens that are all the same as each other get split into a doublet, or their resonance gets split into a doublet by this adjacent red hydrogen. And meanwhile, the opposite's also true. The resonance for that red hydrogen gets split into no fewer than 7 lines because of the adjacent 6 hydrogens. So, but that's very typical for an isopropyl group. So I will admit the splitting is not necessarily terribly easy to see. You might be able to pick out all 7 lines in the septet. If this were on an exam, I would tell you, by the way, there's 7 lines there, kind of like I did there. And same thing with the doublet. I would only if the splitting is, I think, very easy to see, would I not even tell you. But sometimes it's rather crowded like that. And as I've said, I'm not too proud to use ChemDraw to predict the spectrum, since as you saw last week, it can come out very much better. The calculated spectrum can actually come out very much easier to see than the actual experimental data. So, and we'll get to other things. I might mention a few other things that I am not too proud to do on spectroscopy exams. So, right, but so much for diisopropyl ether. We had gone over that one. I wanted to go over at least one example of a compound with aromatic hydrogens. So I chose this p-anisaldehyde here, which we have the spectrum for that here. I pointed out how we would expect to see 4 different types of hydrogen. The aldehyde hydrogen is unique. Those show up around 9 or 10 parts per million. Also, the 3 methoxy hydrogens are one type of hydrogen. I'd expect to see them around 3.5 or 4, give or take. And again, those chemical shift ranges in the textbook are only a guideline. They don't mean to indicate this is where every last example of this type of hydrogen will definitely 100% show up. They're just guidelines. So that's why I do not recommend you spend a lot of time trying to memorize them. But I also am hoping that you all look at enough spectra that you're not needing to look at that table constantly in order to solve spectroscopy problems. It's for things like that sometimes students say they're not able to finish the exams on time. So you have to become fluent enough in the material, so to speak, that you don't need to look up every single thing. And the best thing to do is to just look up a bunch of spectra. And you know, see what you can figure out about them, see what you can pick out. It won't be much at first. Don't let that worry you. Just keep going. I think you'll find that you begin to see patterns then. Anyway, besides the methoxy and aldehyde hydrogen, there's the two types of aromatic hydrogens, the two that are alpha to the aldehyde or ortho to the aldehyde, and the two that are ortho to the methoxy group. And incidentally, I don't think I'm terribly certain which is which. I don't know that I'd expect you to be either, but we certainly can tell that there's two types of aromatic hydrogen, and surely one of them is the ones ortho to the aldehyde, the other the ones ortho to the methoxy group. And again, each of those sets of hydrogens will split the resonance for the other into a doublet because each of them has one adjacent hydrogen. 1 + 1 is 2. But other than that, everything checks out. The methoxy group is here at, let's call that 3.8, exactly where I'd expect to see protons alpha to oxygen. As I said, the aldehyde hydrogen is there at about 9.8. That's perfect, exactly where I would have expected it to show up. And then the aromatic hydrogens are in a range very typical for aromatic hydrogens. Generally, they're round and about 7 or 8 parts per million, give or take a bit, is a pretty typical range for aromatic hydrogens. Now, someone with sharp eyes asked the last time, what about these two tiny little peaks here? How can I know whether or not I should look at those? And since I, at the moment, mostly because I'm inches from my screen, have even sharper eyes than you, if you look really carefully at the aldehyde hydrogen peak, you can see again there's two tiny little lines there. Those are probably what we call spinning sidebands. Not that I really care that you know that's what they're called, but it's an artifact that has to do with setting up the instrument. And it could be that the person that set up the instrument to take the spectrum was in a bit of a rush, or it could also be that no matter what he did, it was going to come out a bit crappy looking. But in general, when you see peaks that are that small in comparison to the main peaks, that's how you know that you can ignore them. When they're really, really tiny, you know, here's another really tiny one over here. So I have been known to put little X's over peaks that you should ignore. I've even been known, I'm not too proud to do this, I've done this in the past and would do it again. I've even been known to take the spectrum into the GIMP or another paint program and white out these little ones that I don't want you to look at so you don't get distracted. I am not too proud to do that, and if necessary, I will feel perfectly free to do that again. So, but if not, or in OWL questions, let's say, if they're really, really, you know, this is not a 1 to 3 to 1 triplet by any stretch. I think you'll agree this is more like 1 to 50 to 1 or something like that. So there's no way those two teeny peaks can be anything of significance. If you see something that tiny, this is part of what it means to get enough experience looking at spectra. And you'll begin to not see little peaks like that, because little in comparison to the main peaks like that. That's a good sign that you can ignore them. But other than that, everything is fully consistent with that. Now, I also don't want you thinking, while we're on the subject of aromatic hydrogens, I don't want you thinking that they're always well separated like that. They aren't. This is why I put the spectrum of ethyl benzene in. I don't think I need to draw ethyl benzene. I think you can handle that. Ethyl benzene, exactly what it sounds like. And you'll notice what happens here is the 5 hydrogens on the benzene ring all fall into this kind of ugly heap. Much better behaved are the protons in the ethyl group, right? Here, I think even if I had not said triplet and quartet, I think you can pretty easily see the 3 lines in the triplet and the 4 lines in the quartet. Nice, well separated. The so-called coupling constant between those is much wider than in some of the multiplets we've seen. So that part at least is much easier to pick out. And again, the methyl group in the ethyl is split into a triplet. By the adjacent CH2 group, 2 plus 1 is 3. So if 2 adjacent protons splits the methyl group into a triplet. And the opposite's also true. 3 plus 1 is 4. The 3 methyl protons split the CH2 group into a quartet. So that's all very easy to pick out. And where does the CH2 come? Around 2.5, very typical for benzylic hydrogens. Benzylic and allylic and also hydrogens alpha decarbonyl, all of them tend to show up round and about 2 or 2.5. So that's exactly where I would have predicted. But the aromatic hydrogens are much less well behaved. Now, we would have expected there to be 3 types of aromatic hydrogens, just as there were 2 in the previous molecule. Here there's 3. There's the 2 that are ortho to the ethyl group. There's the 2 that are meta to the ethyl group. And then there's that unique para hydrogen, para to the ethyl group. So technically, all 3 of those are chemically distinct. The 2 orthos, the 2 metas, and the 1 para. But in practice, they're all so similar to one another chemically, owing to the ethyl group is electron donating. And so it makes all of them so similar that they can't be distinguished. Compare that to when we had an electron withdrawing aldehyde group on anisaldehyde. Now those 2 types of aromatic hydrogen are very well resolved, very well separated. Not so much for ethyl benzene, and that's very typical for like alkyl benzenes and things like that. Then it becomes much harder to separate these 2. So the M here stands for multiplet, meaning I'm not even going to try to say how many peaks are in that resonance. It's not significant even to try. So I would say that's one thing to be on your guard for, is these monosubstituted benzenes, especially when the substituent group on the benzene is an alkyl group or something similar. In cases like that, even though theoretically the aromatic hydrogens aren't all the same, in practice they're so similar that they just fall on top of one another. So what I'm giving you here, now that we've gone through some examples of simple splitting, and believe me, I could have done 20 more, but I wanted to at least give you a few examples to get you started. What we're getting to here is situations where either there's fewer peaks in the spectrum than you would have predicted, or more peaks in the spectrum than you would have predicted. And what are some of the causes of that, so that you're ready for them? So this is one of them. When you have multiple types of hydrogen that should show up in different spots, but they're so similar that they coincide. And this is sadly not all that rare in proton NMR. So the 5 represents all the aromatic hydrogens, right? Meta, ortho, and para, that's right. Which aren't all the same actually, but they're so similar that we can't separate them. They fall all on top of one another. That's not typically a problem with carbon NMR, unless you're looking at something with 100 carbons in it, then maybe. But you know, small to medium-sized compounds up to 10 or 12 carbons or even more than that, you don't have that problem in carbon NMR. Now, I've taken a fair few carbon NMR spectra in my life, and sure, I've seen cases where I'll see one peak at 101.6 and another one at 101.9, and I have to expand that region, and then I can see 2 nice sharp peaks. Yes, something like that can happen. But I don't remember a single time when 2 carbon NMR resonances fell exactly on top of one another. I almost don't think it's possible, just because the chemical shift range is so much wider in carbon NMR than in proton. But in proton, it's not all that rare. And this is one of the reasons that even though you would predict 2 or more sets of hydrogens would show up in different places, they're so similar that you can't tell them apart. And so they just fall on top of one another. And the way you can know that is largely from integrations. So you're not really going to get 5 hydrogens that are exactly identical. They're just all very similar. And so they all fall on top of one another. And in alkyl benzenes, it's not the only case, but in alkyl benzenes, that's an especially common case of that. Would proton NMR be more accurate in identifying a structure than carbon NMR, or should both be used? It's a good question. I would be hard pressed to say either of them is any better than the other. I would say either of those methods is more powerful than IR or mass spec. You know, I said, for instance, can you identify a compound from its IR spectrum? Absolutely not. I would say that's utterly impossible. You can tell what functional groups are there to some extent, or what might even be more important is you can tell what functional groups are not there from the IR. Can you tell what the compound is just from the carbon NMR? Probably not, but you'll have much better luck than with an IR spectrum or a mass spectrum. Now, if you're given a proton NMR, a carbon NMR, and mass spec data, and an IR spectrum, now can you tell what the compound is? Yeah, you probably can. We call those combination spectroscopy problems. And you'll get some practice on those on the OWL, and certainly one like that would be fair game on exam number 4. Within reason, of course. You know, I'm not going to give you something with 30 carbons. You know, it would be something small to medium sized, but nothing really huge. But yes, putting them together now, it becomes pretty powerful. So much for ethyl benzene. But I wanted to give you some other situations when, like I said, either you see fewer resonances than you expected due to things falling on top of one another, or you see more than you expected due to protons that at first glance look like they should be the same, but when you look more closely, they actually aren't. And one such case involves what's called diastereotopicity, or diastereotopic protons. And I've defined the word diastereotopic here in your class notes. And that situation arises when you have 2 sets of hydrogens, usually 2, that at first, if you're not looking carefully, you'd think would be the same, like 2 hydrogens and a CH2, let's say, should be the same. But when you examine the structure more closely, you realize that due to the presence generally of a chiral carbon somewhere right close by, those 2 hydrogens in the CH2 are permanently chemically distinct. And an example is this compound here, minus alpha ethyl phenethyl alcohol, which is a mouthful. But I've actually given you the structure and the what's the word? Assignments over here. Of course, I wouldn't do that in the exam, right? That would be part of the problem in general, right? Figuring out what the compound is, whether you're matching it or you're solving the total structure generally with a combination spectroscopy problem. But if you look carefully at this structure, and again, one thing we see immediately is look at this big heap at about 7.2 that integrates to 5 H's. Well, again, that's all 5 of those aromatic hydrogens that really aren't all exactly the same. You've got your orthos, your metas, and your paraproton, but they can't be distinguished because we've got an alkyl group attached. And surely we'd expect the CH3 to be one type, this CH2 to be another type. This proton they've labeled B, that's sometimes called the carbinol proton, not carbonyl, carbinol, C-A-R-B-I-N-O-L, meaning the proton that's alpha to an OH group. That's a thing by itself. The OH hydrogen is a thing by itself. By the way, good luck ever knowing for sure, at least from first principles, which is the OH group. I'm sure in your textbook in that table, it'll give you some completely bogus chemical shift range for OHs, like 1 to 6 parts per million or something like that. Truth is, OH protons can be anywhere if you can even see them at all. Sometimes they're so broad that they just disappear into the baseline. And I'll just let you know, I've made many an alcohol in my life, and so had to take a spectrum of the compound to prove that I made what I thought I made. And if it's any help at all to you, I always identify the OH proton last because the others are always so much easier. So I get the OH one by process of elimination. That's generally my strategy with OHs. Get the others first, and whatever is left is my OH. Same thing is true of carboxylic acid protons, except they can't be absolutely anywhere. They're going to be quite far downfield. But I would say anything in the 10 or 11 to 15 or even 16 range is fair game for a carboxylic acid proton. And a similar thing happens with NH protons in primary and secondary amines. They can be anywhere and they can be stupidly broad. I've had cases where I had to integrate over like 3, 4, 5 parts per million to find my one NH proton somewhere in there. So they can be very difficult to identify, and they can also be just about anywhere. But once we move on to the next proton, the next set of protons, you think, oh, well, a CH2, so won't those two be the same? Well, not so fast. The reason is, of those two hydrogens, even though there's full freedom of rotation around all of those single bonds, in fact, those two hydrogens are permanently chemically distinct from one another, because at any one moment, one of them is going to be closer to this OH group than the other one. And so although you'd expect them to have the same chemical shift, in fact, they don't. And you can see where they show up here, and you can distinguish them over here. And that's why I left the assignments over here. And that's why some of these resonances look so ugly, because you have hydrogens that are distinct from one another, but close enough that they just fall on top of one another, and you get these really ugly looking resonances. This happens quite a bit in cyclic compounds also. Like if you're looking at cyclohexane or cyclopentane derivatives, those hydrogens generally don't come out to be nice triplets and quartets and things like that. The methyl group's not bad, I will admit. That's pretty clearly a triplet. This resonance is kind of pretty. Is that the carbonyl proton? Let's see, is that B? B is at 3.69. Yep, that's that one. And so, goodness, how would that one be split? That could be split by the CH2 into a triplet. And then, in principle, each of these two in the CH2 can further split those triplet lines. So you could get a triplet of triplets. You could have as many as 9 lines. I don't think we can see 9 here. I think we can see at least 5. Maybe if we had a better instrument, we could see more than that. And if we expanded that region, we could see more lines than that. But that's then another type of complex splitting. When you have, and I'll give you a simpler example next when we look at 1-pentanol. But before we get on to 1-pentanol, and again, as you know, I try to keep all of this as results-oriented as possible for you guys, just so you know what it's like in the field when you get diastereotopic protons. If it's any consolation to you, the few times it's come up in spectra that I've taken, it almost always takes me by surprise. I should see it coming, but I almost never do. What will happen in practice is I'll take a spectrum of some compound, and a proton spectrum, and it'll look just terrible. You know, it'll look like this. And I'll go, what on earth is going on here? I thought I purified this compound. You know, I thought I did a column chromatography or whatever, and it was extremely pure. And then all of a sudden, when I look more carefully at the structure, it'll just hit me. Oh, hell's bells, they're diastereotopic, and that's why it looks like that. So it's often something you figure out kind of after the fact. But it's something to stick in the back of your mind as a possibility, and Al will give you some practice in those as well, since now we can finally finish our chapter 13 owls. So diastereotopic protons, and again, I've defined the word here in the class notes. That's one case where things can come out looking different than you would have expected, when in that you see two sets of protons like these two here, which you think at first, well, that's a CH2, they're the same. No, they're not, because due to this chiral carbon right next door, even though you've got full freedom of rotation around all of those single bonds, always one of those hydrogens is going to be nearer in space to the OH group than the other. And so in fact, they're permanently chemically distinct enough that they have slightly different chemical shifts. So that's what we mean by diastereotopic protons. And it's just one thing to be aware of. It's not something you'll run into very often, but I also can't promise you that you won't run into it. It's something that does show up from time to time. And it means that you have to be flexible. It means we use this N+1 rule when we can, but we have in the back of our mind that things may either look more complicated than that, or they might look less complicated also. That it will work out probably 90+% of the time, but not 100. So that's one situation. Another one that can show up is when you have more lines than expected, or more peaks than expected, due to a set of hydrogens having multiple different types of adjacent protons. And I'm thinking in particular of this CH2 group in 1-pentanol. It's tempting at first to say, well, there's 2 H's adjacent over here, 2 more over here. That makes a total of 4. 4 plus 1 is 5. Those 2 hydrogens should be split into a pentet, 5 lines, right? Well, not necessarily. And this one, I actually calculated the spectrum using ChemDraw, because I looked up the spectrum of 1-pentanol on this website, and it looked absolutely dreadful. So this looks much better than the spectrum that they had for me. So if we look for that CH2 over here, it says it's at 1.58, so here you go. And I think you'll see it's not just 5 lines, it's way more than that, nor is it a nice even, what, 1 to 4 to 6 to 4 to 10 pentet. There's other fuzziness going on in there. And indeed the same thing for the other two. Well, the methyl isn't horrible, but it's also the methyl is affected. That may be some long range splitting, maybe some splitting over more than 3 bonds. That can sometimes happen. And I mean, this one here, what a mess that haystack is. That's likely because you've got multiple types of adjacent hydrogens. And so it's not always the case that you could just simply add them all up and then add 1. You might get more splitting than that. Certainly that triplet's very nice. That's going to be the CH2 alpha to OH. You'll notice the OH does not split this further. This simply has the 2 adjacent protons over here. 2 plus 1 is 3, and it's a nice clear triplet. And that's pretty common. The reason that OH protons usually don't split adjacent protons is because OH protons, really any type of proton that's protic, right? So attached to oxygen or nitrogen directly, those undergo very rapid physical exchange, meaning that faster than the NMR timescale that it requires to take the spectrum, they are literally moving from molecule to molecule. They're literally getting swapped between molecules. And so for that reason, it's very commonly the case that OH protons will not split or be split by adjacent hydrogens. They're very confidently, by the way, saying that the OH proton shows up here at exactly 4.7. I think that's kind of cute. And it might, under some circumstances. It turns out in the other alcohol, the OH hydrogen is here. And they often appear rather broad like that, but in either case, I guarantee you, if you used a slightly different concentration in the sample, or it were a particularly hot day that you took the spectrum, that OH peak can move arbitrarily to a different location. That's why, as I said, I always identify the OH protons last. I get everything else first. Everything else is easier to assign, and then whatever's left is my OH. That's generally how I go about it. But this is a case where you've got more complicated splitting than just N+1 rule would lead us to guess. And that's because you have more than one type of adjacent proton. So you can't just lump them all together. 2 plus 2 is 4, 4 plus 1 is 5. It may not be that simple. So these are just some of the things you can look for. And I mean, I could go on and on and on with examples of these things, but I wanted to leave time for the reef questions, and then maybe to begin chapter 26 in carbohydrates. We won't get very far today, and we don't need to. Just so if it saves me, so I've another 5 to 10 minutes to talk about some of the structural particulars of carbohydrates, so much the better. But obviously, if you guys have other questions today on proton NMR, you may feel free to ask them. But that, I think, again, at least will get you started on the chapter 13 OWL homeworks. Well, actually, I hope that most of the chapter 13 OWLs you've done already, because they're on carbon NMR or IR spectroscopy or something we've already done. So, if you've left the proton NMR problems until now, that's completely fine. And so now will be a good time to finish them. Good. So like I said, my going on is not meant to indicate that I don't care about your questions. You can feel free to ask them in chat or unmute yourself for a moment if questions pop up. But that's a good place for us to do our reef questions. So I have them already over here. So please register your attendance by all means. That will be 80 of the 100 points for the day. That will all get averaged at the end of the term. And by the way, don't forget that I'll be dropping at least the lowest 25% of your reef grade, since there's always unexplained crap that happens. Your answer doesn't register, or your cell phone's on the fritz, or stuff like that always happens. So that's why I do that. Good. So question 1 is a chapter 23 type of thing. Let me get these out of the way so you can read it. It basically says, and I'll start it in a moment, enamines behave like blank towards blank. So your goal is to fill in those 2 blanks. And we'll go for about 2 minutes. But I think one of those is the best way to finish the sentence. Looks like that's it. All right, well, one of the things you hopefully got out of the latter part of chapter 23 is that enamines are very much like either enolates or enols. You could think of it either way. There's great similarity between or amongst all of those types of compounds. Enamines are a very good nucleophile, and like enolates, enamines prefer to add to the beta carbon of an alpha-beta unsaturated ketone or aldehyde. So that was the Stork-enamine reaction. So I think the best one is A. They act like enolates do towards conjugated carbonyl compounds. So I think A is the best answer. And you guys thought the same. Good. One more from NMR stuff. Again, let me move everything out of the way here so you can actually read it, including my weird face. There we go. So which of the following are things that proton and carbon-13 NMR have in common? So of those 5 pairs of items, 2 of them are something that carbon and proton NMR have in common, and the other 4 ain't. So you want to pick the one that do and not the 4 that don't. I don't know which is more upsetting, when there's fewer responses to the second question than the first, or more. This looks like the case of fewer. All right, looks like that's everyone. So, well, let's look at each one of these. Again, we're looking for 2 parameters that work pretty much the same for both proton and carbon NMR. Chemical shift and spin-spin splitting. Note, spin-spin splitting is by and large cat pictures. Oh yes, yeah, those are not my. Oh, I've had those for years. I have others elsewhere in my house. I picked those up at some store. Yep, so one of them's a calico cat. Actually, one of them is Barnaby, isn't it? So one day I want to have a calico or a tortoiseshell cat. I've always wanted one. Anyway, not while there's a Bella, that's for sure. All right, so spin-spin splitting is purely a proton NMR thing. Spin-spin splitting and peak integration, no, those are the two things that distinguish proton NMR from carbon NMR. Peak integration and nuclear equivalence, well, nuclear equivalence, yes, that's something that we have in both. But peak integration, again, is something we pretty much can't use in carbon NMR. Chemical shift and nuclear equivalence. That sounds pretty good. Both of those have that. Let's make sure and look at E. Nuclear equivalence and spin-spin splitting. Note spin-spin splitting is something that applies just to proton NMR. So I think D is the best answer, as did you guys. Good, so you didn't, so good for you. You didn't let section 513 put you to shame. I knew you wouldn't, I knew you'd be fine. Good, so of course the remaining 80 points are just from attendance. So please register your attendance if you have not done so. While I'm at it, it was A followed by D. So let me just make sure I get those in there before I upload. Good, so where are we at? We have 5 more minutes, that's good. Let's look at essentially the simplest compounds that we can say are like, are at all carbohydrate-like or sugar-like. And I think you really need at least 3 carbons to be able to get to that point. So back in chapter 5 or something like that, when we first started talking about chirality, we would draw things like this. I've started to call these pre-Fissure projections. And the reason is actual Fissure projections are built on structures of that type. So this type of drawing, and this of course only has 3 carbons, but this type of drawing is what we mean by a Fissure projection. And your book is the first one I've seen that puts off talking about Fissure projections until the chapter in carbohydrates. It sort of threw me off at first, but now I'm a big fan of the idea. I really like it because traditionally we introduce Fissure projections, not to be confused with Newman projections or with Hayworth projections, which are both different, are both different critters. They usually would do that back in chapter 5 with the result that in the next semester, you know, some 6 months later, we get to carbohydrates. And I would say, y'all remember Fissure projections, right? And they're going, huh, what, who, where? So I think this is better. So recall this is one way of drawing chiral carbons. A Fissure projection simply abbreviates that even further. So you just need to remember in Fissure projections, all horizontal bonds are wedge bonds and all vertical bonds are dotted bonds. One other extremely critical thing about Fissure projections is you'll notice that I did not put a letter C at the intersection there. That's very important. As soon as you put letter C's at the intersections, it is not a Fissure projection, and you've just wiped out all the stereochemical information. It's a correct structure. You know, carbon still has 4 bonds, that's all good. But you must not put letter C's at those intersections, or it's not a Fissure projection any longer. So those are pretty much the only things by way of convention with Fissure projections. And glyceraldehyde is a 3-carbon sugar, and what makes it a sugar, I would say, is the aldehyde group and the OHs. And basically that's true. Carbohydrates are just polyhydroxyaldehydes and ketones, period, full stop. And we know about hydroxy groups. We've known about alcohol since chapter 17. And we've certainly studied ketones and aldehydes quite a bit over the last number of chapters. So unsurprisingly, when it gets to the structure and reactivity, and wherever possible the mechanisms that involve carbohydrates, it's going to be the very same reactions that we know already. So that's what we're going to largely get into starting Wednesday and then also on Friday. So what makes it D versus L glyceraldehyde is the so-called penultimate OH group, meaning the OH group that's just before the CH2OH group. And by convention, so-called aldoses, meaning sugars that have aldehyde functional groups, By convention, we put the aldehyde group at the top of the molecule, and that last CH2OH, which there will always be one, at the bottom of the molecule. And so it's the second to last OH group that determines whether you're looking at a D or L sugar. D sugars have that OH group on the right, and L sugars have it on the left. And again, it's going to be your D sugars that are natural and your L sugars that are unnatural. You can get L-glyceraldehyde, it's a thing that exists, but it needs to be made in the lab. It's not a naturally occurring compound. And so, as you would predict, very much more expensive than D-glyceraldehyde. And so if we understand about D and L sugars, we're going to be fine even getting up to D and L glucose, which is coming up next on Wednesday. I would say if I had to mention one more simple 3-carbon sugar, it would be 1,3-dihydroxyacetone, which is this guy here. It's exactly what it sounds like. You know what acetone is. Acetone is the smallest possible ketone with 3 carbons in it. So dihydroxyacetone, 1,3-dihydroxyacetone, simply has OHs and carbons 1 and 3. And that's the simplest possible ketose. It's a cousin of fructose, for what it's worth. But D and L glyceraldehyde and 1,3-dihydroxyacetone really are the smallest molecules that we can say are sugar-like. So you need at least 3 carbons to get a molecule that's at all like a sugar. And it goes up from there, 4-carbon sugars. We know a 5-carbon sugar. Actually, we know 2 ribose and deoxyribose, 2 deoxyribose. So we're after this going to mainly focus on 6-carbon sugars, mainly glucose and its 7 family relatives. So we can start on that next time. I just wanted to get us started with 3-carbon sugars this time. Do you have to know the structures of D and L glyceraldehyde? Yeah, I think that's going to be helpful later on, especially, not to mention that you can't look them up, but I would become familiar with the structures of D-glyceraldehyde and L-glyceraldehyde. I'm not really so concerned about any of the 4 and 5-carbon sugars, well, maybe except for ribose in its cyclic form. When we get to the D-aldoses, the aldohexoses, so the 6-carbon sugars that have an aldehyde group and that are all in the D form, you'll find there's 8 of them because there's 3 chiral carbons. There's really 4, but one of them is invariant because we need the D sugars. So that OH must also always be on the right, but that leaves 3 chiral carbons. And you remember 2 to the power n, there's 3 chiral carbons that can vary. 2 cubed is 8. So there's 8 of them. I'm only really going to ask you to learn glucose. Those of you going on to biochemistry might well have the pleasure of learning all 8 of them. I'm really fine with your just learning glucose. And I'll make this point on Wednesday, because for my money, if you know glucose, then in principle, you know all the other 7 too. So we'll get to that on Wednesday, but that I think is a good place to stop today. So I'm out of time. I need to let you guys go. Have a good day. I will try to get this, this video up later today or tomorrow at latest. And also some sleep, I think, will be well called for today. But have a good day. I'll see you all on Wednesday.